Let's talk about continuous functions. And at least at the time I'm making this video, this is the last topic that is on our assignments before we have our next test. Okay? So continuous functions. Part of the idea is very simple. In fact, you might say it was entirely visual. So I've drawn the graphs of two functions, and one of them is continuous at this point A, and the other one is not continuous at this point A. And what that would mean visually is that the graph was solid in one piece with no displaced or disconnected points at the spot in question. So this point A on the x-axis, that graph is totally intact. It's not disjointed. You know, some of it here, some of it up here. There's not a point separated from it at that spot. There's lots of ways a graph could be not continuous, but if it's continuous, it's solid and in one piece at the point in question. So this graph is continuous, this function is continuous at the point where x is equal to a, but it's continuous everywhere else also. But we normally talk about a function being continuous at any particular spot, okay? And then this one is not continuous at the point where x is equal to a. You know, it's in two pieces. It's split in two pieces right there. It's not solid and in one piece at that point, x is equal to a. So we would say this function is not continuous at the point x is equal to a. Okay, so you've seen what continuity looks like, and this is just one way that a graph could not be continuous. You could also have a graph where like it seems solid and in one piece, but at this particular spot, a point is displaced from the rest of the graph. That would be another example of a graph that's not continuous at a particular spot. Now, so visually the idea I think is pretty simple. As far as the math goes, here's the math. Okay, so as far as just math, no pictures or images or anything like that. What would it mean for a graph or function to be continuous? Okay, well, so this is just the math. A function is continuous at a point x is equal to a if the limit as x approaches a for that function is equal to the value of the function at x is equal to a. So the limit as x approaches a for f of x has to be equal to f of a. F of a is what you get when you plug a into the function. So if I was going to illustrate this math for this one, here's what I would say about it. Okay, I would say the limit as x approaches this number a right here for our function actually does not exist. Because what does the limit as x approaches a mean? It means that if x is close to this number a, what does that put y close to on the graph? Because on the graph there's x and y. Every point has an x and y. Let's say, well, if x is close to a, that doesn't put y close to any one number. If x is close to a on the left, then that will put y close to 5. Okay, like these points are all have a y coordinate of about 5. But if x is close to a on the other side, that's going to put you up here, and all those points have y coordinates close to 7. So if x is close to a, that doesn't put y close to any particular number. So the limit does not exist. It's like saying the limit doesn't have an answer. Okay, that's the limit. That's this part. But what's the function value? What's f of a? Well, okay, so f of a is what I get out of this function if I plug in the number a for x. Well, plugging in a for x would correspond to this point right up here. See how this point's open? That means that point is not really on there. A for x and 5 for y is not on there. The function goes right up to that, but doesn't quite get to 5. All right? So that would, f of a would correspond to this point where that point is bold. It's filled in. And it says when x is a, y happens to be 7. All right. So look, the limit at a is not equal to the function value at a. Does not exist is not the same thing as the number 7. See how these aren't the same right here? Not equal? Okay, that's what I'm saying. If the limit and function value are the same, it's continuous. If they're not the same, it's not continuous. Okay? Now that's the math. Visually, you can look at it. You can tell it's not continuous. It's not solid, and it's not in one piece. But, you don't always have access to the picture. The picture might be too complicated to draw with any amount of detail. All right? All right, now let's run through some examples. Here's one that's similar to what I was just talking about. This point, this looks like it would be continuous, except for this point being displaced from where it seems like it ought to be. It seems like it ought to be down here, but that point's displaced up there. It seems like it ought to be near 3, but it's up at 5. But let's answer these questions and decide if it's continuous. So first of all, is it continuous at 2? Answer is no. Okay, it's not, and I can tell just by looking at it that it's not continuous at 2. But there is some math that we need to be held accountable for too. So that definition I just read you said if this limit and this function value are the same, this graph would be continuous, and if they're not, then it's not continuous. And I can tell by looking at it that it's not continuous. So I know that whatever I get for this limit is not going to be the same as the function value. So let's do each one and show that that's the case. What's the limit as x approaches to f of x? So what that would mean is if x is close to 2, what is y close to? So look at this graph. Look at all the points on it. And if x is close to 2, y will be close to what? Now, close to 2 just means, near it but not equal. So if you're close to 2 on the right, that'll put you up a little bit more than 3 for a y coordinate. And if you're close to 2 on the left, that'll put you a little bit less than 3 on that graph. The y coordinates will be either a little more than 3 or a little less than 3 accordingly. So I'd say, well, the limit as x approaches 2 is 3. On that graph, the closer the x is to 2 on either side, the closer the y will be to 3. Okay, so there's my limit. But what's the function value? F of 2. What does f of 2 mean? It means on this graph, according to this function, if x is equal to 2, what is y? Well, here we're not asking what happens when you're close to 2. We're asking what happens when you are 2. Well, when you are 2, when x is 2, that corresponds to this point right here, where y is 5. Okay? So the function value and the limit are totally different. This asks what happens when x is close to 2, and this asks what happens when x is 2. All right? So I get 3 in one hand, I get 5 in the other. And those aren't the same thing, and so the function's not continuous. Now, do you see why the definition is like that? Do you see why these two would have to be equal for it to be continuous? Well, what if they were equal? Then it would be like saying, well, the point you get when you're close to 2 is the same as the point you get when you are 2, because the limit, the arrow, refers to what happens when you're close to 2, and the function value asks us what happens when you are 2. Well, if I don't get the same thing, then that means that I'm like part of the graph is up here away from the rest of it. Okay? All right. So let's try now this one. This is called a piecewise function, meaning what the function is actually depends on what x is. So if we look at our last example, then, or let's say, like a typical function that we have that we've been dealing with. I don't know, f of x is equal to x squared minus 1. Then that's one formula, no matter what the x is. No matter what x is, you plug it into the same formula, no matter what. And that's how you get your y coordinates and your points in your graph. But a piecewise function gives us different formulas depending on what x is. So here, the way I'd read this is it says, well, x or y is 2 if x is less than or equal to 0. So anytime you put in an x less than or equal to 0, 2 is your answer. 2 is y. And then this middle one says if x is anything between 0 and 3, then y will be the x plus 3. Okay? All right. And then if x is 3 or greater, y will just be 6. All right. So that's how I would read that piecewise function. And here I have various limits and questions about continuity. Let's do this. Let's start by drawing the graph. Okay, so that's what I'd like to do first. Okay, so let's see. The way I would sketch this graph and have an image to go on to answer these questions, so I would do one of these at a time. Like, so for example, this middle part, y equals x plus 3 if x is between 0 and 3, is like a graph all by itself. So look at it like this. If, let's plot some points. If x is 0, 0 plus 3 is 3. So that would give me this point. Okay? And if x is 3 on the other end, y would be 6. So that would give me this point. See? And then it's a line otherwise, and you're going to see that all the other points, like if you could graph, what else is there between 0 and 3? 1 and 2. Then 1 would give you like this point right here, and 2 would give you this point. And this is what you would get, okay? All right, so that's just the middle part. In the piecewise function, we've got to look at it like every part of this function for these various values of x exists on its own, okay? All right, next thing, why do I put these open circles here? Well, notice how like I plugged in 0 into that and I got 3 and I put a point there. And then I plugged in 3 for x in here and I got 6 and I put a point at 6. But I put them to be open because is 0 actually included in this rule right here? What's this rule say? X is greater than 0, but also x is less than 3. 0 and 3 are technically like they're not allowed. They're the endpoints. So it's okay to use these endpoints to draw the graph, but I have to consider that they're not really on there. Like technically I'd have to pick a number, like I'd have to pick 2.9999, but that's kind of an awkward number to work with. So I pick 3 and I make it open. And I pick 0 and I make it open. So there's that middle part. Now these other two may pick up where this middle one leaves off at, or they may not, okay? So let's go from here. Like, does this one pick up where that one leaves off? So this one picks up at 3. This one leaves off at 3. And what does it, y coordinate do you get? You get 6. So the very first point on this last one is 6. So it picks up exactly right there where this one left off at. And then it's a horizontal line from there on. Okay, because if x is 4, y is 6. If x is 5, y is 6. If x is anything bigger than 3, y is equal to 6. So it looks like that. What about this one? Does this one pick up where this one leaves off at? Well, this says y is 2 if x is 0 or less. So let's see. Here's where x is 0. That would put me at 2, right? So I'd get this point and be filled in. Oh, it's not connected, that one. This one left off at 3, and then this one picks up at 2. Okay, well, they're not going to meet in the middle. This one of them's not going to pick up where the other one leaves off at. So anyway, I'm going to get like this. Okay, if x is negative 1, y is 2. It's going to be horizontal. If x is negative 2, y is 2. If x, for anything less than 0, y is 2. This one does not pick up where that one leaves off at. And so there's my graph. All right. It's continuous here, but it's not right there. Okay. All right. So that's how I would think about a piecewise function. Now with the graph at hand, let's answer some questions about it. First one says, what's the limit as x goes to 0 from the left? So look at our graph right here. And what happens to y if x is close to 0 on the left only? That's what, remember this when we learned limits earlier in the semester. That's not a negative necessarily. It means from the left. And this plus, this superscript plus means from the right. So I would say that if x is close to 0 on the left, that would put you up here, which is right at 2. So this limit is 2. Okay, so there's that one. And what about x approaches 0 from the right? Okay, if you're right of 0, that would put you right up here. And where did we put that point? And then where are these nearby points located as a result? they're going to be about 3. So if x is close to 0 on the right, then y will be close to 3. So the fact that these are different explains why like it's not continuous. So if I couldn't see the graph, if I covered this up and I saw this and I said, well, here's what this curve looks like. Left of 0, you're near 2, but right of 0, you're near 3. That tells me that it's not, whatever it looks like, it's not meeting in the middle there at 0. Okay? All right, so let's see. What's the limit as x goes to 0? Does not exist. Okay, whenever these two one-sided limits don't agree with each other, the limit at all doesn't exist. If you're just close to 0, it doesn't put y close to any particular number. So that's the time when we say the limit does not exist. What's f of 0? So that's the function value. It says, what do you get out of this function when you put 0 for x? Well, when you put 0 for x, according to this right here, if x is less than or equal to 0, y will be 2. So you'll get 2. You can figure it out that way. But also you can look at the graph and I can say, see that point right there? That's 0 for x, 2 for y. Okay, yeah, so it says that the fact that it's bold and not open says if x is equal to 0, y is equal to 2. So, okay, yes, it's 2. The function value is 2. Is it continuous at 0? Well, no. I mean, this math up here justified that it wouldn't be, but you know, if I could sketch the graph for you like I did, then that also shows that, you know, look, see that gap? You see how the graph is disconnected from itself at 0? Well, that's how we know it's not continuous, okay? We can either look at it, the fact that these two numbers are different tells you that. The fact that these two numbers are different tells you that also. The fact that you can just look at it tells you that it's not continuous, okay? All right, now let's do, I wanted to look at this other point because you see how whenever we have a piecewise function, the places where it might not be continuous are where these formulas leave off and pick up at. Like this one leaves off at 0. Then this next one picks up at 0 and goes to 3. And this next one picks up from 3 onward. Okay? So if this graph wasn't continuous, I would expect it to be either 0 or 3 or neither or both. It just depends. So we looked at the 0 and I calculated some of the limits by inspection of the graph and determined it wasn't continuous there. And now I want to look at this other point, 3, okay? So let's see, like, now here I'm not going to draw the graph again. There's the same graph you just saw me use. Okay, so look at the graph. What's the limit as x goes to 3 from the left? So remember, that's not a negative number necessarily. It means from the left. Well, so there's 3 right here, okay? And this is 6, okay? So that's where we put that point when we drew the graph. And you know, whether you're left of 3 or right of 3, you're going to be in the vicinity of this. So here's another way we can think about these points. You see all these points here? Every single point in that vicinity has x to be about equal to 3, very close to 3, and y to be about equal to 6, no matter what, okay? So whether you're left of 3 or right of 3 for x, it's going to put the y close to 6 either way. So there's my final answer on both of those one-sided limits, okay? And if the one-sided limits are equal, that makes the limit, you know, as is, x goes to 3 equal to the same number. All right? So yes, you know, if you're on the left, y will be close to 6. If you're on the right, y will be close to 6. What's this mean? If you're anywhere close to 3, y will be close to 6. So it's like this one contains those two together. Okay? And so long as these are the same, that will be what you get. What about f of 3? What about the function value? Well, real quick, what do we expect it to be? Because look, is it continuous at 3? Yeah, I mean, it's in one piece. For sure, that graph is continuous and solid and in one piece at 3. Yes. So what would you expect this to be even if you couldn't see the graph? well, let's go back up to the beginning. We said if a function is continuous at a point, then the limit and function value are the same at that point. So now it looks like I know it's continuous, and I know what the limit is. And I know for it to be continuous, they have to be the same. So the function value would have to be 6. Okay? Is it? Yeah, I mean, right here, if you just look at that formula, the actual mathematical formula for this function, if x is 3, that wouldn't fall into this, and it wouldn't fall into the middle one, it would fall into the last one. The last one is for x greater than or equal to 3. So if x is 3, it says y is 6. Okay, yeah, so f of 3 is 6. But if you look at the graph, see that point right there has me at 3 for x exactly and 6 for y. So either way you look at it, that's what we get. Okay, so let's see an example of when we have a piecewise function that might not be continuous. You've seen like flat rate pricing before, so if you've ever seen any kind of flat rate pricing, then you've seen something like what we have previous in this video. And so let's give, now I've like simplified an example a little bit from something I put on the My Math Lab assignment, but let's say that it goes like this. Because of a bulk discount, meaning the more you buy, the less the unit price of some item is, the price of a commodity is as follows. Okay, the price in dollars per pound, given that X is the weight you buy in pounds, is 60 cents a pound up to 100 pounds, 50 cents per pound more than a 100 up to 200 pounds, and 35 cents a pound if you buy more than 200 pounds. Okay. Now I ask about that, if you could consider this to be a function or a graph or whatever. This is just something that determines how much we're paying per pound for some commodity, but would it be continuous at the point where x is 100? Would it be continuous at the point where x is 300? Well, how about this? I've been doing things by graphs. If you don't like the graphs, you don't have to draw it. Nobody's going to make you draw it. But that's what I'm going to do because I think it would have the widest appeal. Okay, all right. So I'm going to draw this graph. So here's P of x being the price in dollars per pound, and x is the quantity that you buy in pounds. And I see that like 100, let's do this. Let's do 50, and then 100, and then 150, and then 200, 250, and 300. Okay, and that's more than what we need. And we'll do, let's see, let's put 0.5 here. And then this will be 0.35 roughly. And then this will be 0.6. Okay, so here's what I'm getting out of that function. If x is between 0 and 100, p of x or y will be 0.6. So that would be a closed point here and a closed point there, wouldn't it? So why closed points? Because when x is 0, see it has this greater than or equal to. When x is 0, y is 0.6. When x is 100, y is 0.6. Okay, so that's how we get those. Okay, now to continue and draw this middle part, it says if x is more than 100 but less than or equal to 200, then p of x or y is 0.5. So that means if I go to 200, I'd have to have this open point, okay? And then close it in, because that says less than or equal to. And then I'd go over to 100, and I'd have to put an open point at 0.5, because if this doesn't allow me to have 100, but it's like saying if I had 100.01 pounds, the price would be 50 cents a pound. All right, so it's got to go like that. I'll go right up to 0.5 for x is equal to 100, but I have to have it open at 100, all right? So then I get like this. That's that middle part. And then this last part says if x is more than 200, y is 0.35. So again, that's more than 200. If that was greater than or equal to 200, then I would put in a bold filled in point right there, but it's not. So at 0.35 for 200, that's got to be open and so on. All right, so this is what it would look like. Okay, and then I have an arrow going indefinitely that way because it just says x is greater than 200. All right, now I did the best I could without graph paper. I know, like, now that I've got it drawn, it looks like this is skewed somewhere. That should be right above 100. Maybe that bothers me enough. You could always just fast forward a little bit if you wanted to. So I'm going to fix this because it's bothering me. Okay, I'll get there. Okay, so this will be a little bit more like it. I'm going to go like so. That point's bold, going over like this. And then this point is open, going over like that. Okay, that's more like it. Okay, so that's right above 100, open and closed accordingly. And then this is right above 200, open and closed accordingly. All right, so I've got it now. There's my graph. This charts the price per pound for various number of pounds bought of this commodity. Now, now that we're looking at that, if you can agree with my graph, would it be continuous at the point where x is 100 versus 300? Well, I mean, look what we're trying to examine. You know, is it continuous here? Okay, so this is the point where x is 100. Versus, is it continuous like over here? This is the point where x is 300. Well, okay, so it's not continuous here. There's an obvious break, so no for that one. Final answer. Okay, and at 300, it's just going to be one solid horizontal line at 35 cents a pound from 200 onward. Okay, so I don't see any reason at all why there would be any kind of break in the graph over here. There's no other breaks. We're not jumping from 60 to 50 cents a pound to 35 cents a pound. There's no more jumps after that. No more places where it would possibly not be continuous. So knowing yes accordingly. Now, of course, like if you've got a mind to, some people have a good imagination with math, right? And they can kind of see all this in their head just from the formula and tell you right away that it's continuous at 300, but not at 100. Okay, so that's no big deal. I'm not saying you have to draw the picture, but if you're having trouble making sense of this formula when you just stare at it, here's how we're saying the price drops abruptly through various amounts of the commodity that we buy, all right? But it's exactly according to this formula. And if you can see that, I think it makes both of these questions pretty easy to answer.